Thank you very much, Mark. First of all, my voice has not been what it normally is, so I'm going to do my best to project. But if I sound like a teenager, I'll go with it. I also just asked Mark something that was important. I have a lot of material I'm going to show you here from some data over the past couple of years and current information. And I wouldn't try to stress too much about writing it all down. I'm going to provide a PDF to Mark so he can share that with you later. But my role here is to really talk about kind of where we are in the state of the climate, both looking back at this past year, talking about current conditions, and then looking into the short term. So I'm going to try to talk about what we experienced and what I think, or at least what the evidence right now is showing me coming up for this current growing season. So the first piece of this is we're going to look at global temperatures in 2019. All of the data just got released from all of the major agencies worldwide, and 2019 ended up to be the second warmest year on record, and the last 5 years are now the warmest ever that we've seen on the planet. However, I want everybody to note, see that big blue mess right there in the middle of North America? Something important to talk about. The only major region in the world, landmass region, that was relatively cold. So it's a very important point that we'll come back and touch on quite a few different times. 2019 was also the warmest year ever in the world's oceans. Temperatures both at the surface and with depth are warmer than they've ever been. And 2019 was also the warmest year for the Arctic ever, and both poles are losing ice mass at record paces. The current trend over this, and this is what I'm trying to show here, is that all of the global agencies collecting data are all lining up in terms of their records. Europe, America, Japan are all lining up in terms of where we are. You can see where the end point there is for 2019, just over 1 degree Celsius or nearly 2 degrees Fahrenheit above average. If we look at just the United States, the continental United States, this is what our average temperatures were for the year. We ranged from 1.2 degrees Fahrenheit below average in that core area of the northern plains and kind of the upper Midwest to 2.7 degrees Fahrenheit above average down in the southeastern part of the United States. On total, the United States was above average in general, with the southern part being a little warmer than the northern part. And this was the 23rd consecutive year that the continental United States was above average. And by the way, I don't have Alaska in here, but Alaska just experienced their warmest year on record as well. We'll talk about that a little bit more as well. One of the things that shows up, and I don't have the actual diagram for it here, but just to give you a sense of this, minimum temperatures were up much more than maximum temperatures in 2019. And this has continued a trend that we've been seeing for quite a few years. And probably the biggest cause is we think that a warmer atmosphere, just like anything, would hold more moisture. Therefore, there's more evaporative potential coming out of bodies of water. So we tend to have higher minimum temperatures. We'll definitely talk about that relative to kind of where we are today as well. So this is some data from California. This is just looking at June to August. This is 1895 to 2019. Statewide, the trend is 2.3 degrees Fahrenheit over that period of time. And all divisions, if you look at the map on the right-hand side, these are the climate divisions that the U.S. uses in these areas. The trends range from about 1.8 to 3.1 degrees Fahrenheit since the late 1800s. You can also look at it from a distribution standpoint. I like to put it in this kind of framework because you can kind of benchmark things on it. If you looked at the entire time period that we have data for California's growing season, we could say that our distribution is relatively normal, of course. But if you look at the information, since 1995, only 1999, 2010, and 2011 have been below the mean of the last 30-year normal. 2010, you guys all remember 2010, relatively cool year. It was 1.6 standard deviations below the average, while 2012 and 2018 ranged from 2.3 to almost 3.1 standard deviations above average. 2019 ended up right here for California, right at 1 standard deviation above average. If we move over into precipitation, this is just the percentiles for the year, going from green being very wet to brown being very dry. For the continental United States, this was the second wettest year on record. Most of it had to do with the upper Midwest, Ohio River Valley and Great Lakes region seeing huge snow inputs in the spring, and then we had quite a bit of rain following that up and a lot of flooding, of course. I just said that. California was above average, second year in a row, and the Pacific Northwest, Texas, and the Southeast was below average. If you look at the California overall framework for annual precipitation, there are no trends over the past 120 years. There are some minor trends in seasons and in some regions, but they're very, very minor. Mostly we've seen just a lot of variability in precipitation. Past couple of years, it pulled us out of a prolonged period of dry conditions overall. Now, before I get into this, I need to take a drink of water here. This diagram is a little complicated, but I think it'll lead into a lot of what Thibaut is going to talk about in a little bit. But I need to describe it. This has multiple different things on it. On the right-hand axis, it has average temperature departures from normal. And when I say normal, normal means the last 30-year climate average, which was 1981 to 2010. The gray line is the day-to-day departures from zero. The red line is the zero line there. And then the black line is the weekly moving average. So you can see where it was warmer than average, colder than average, so on and so forth. And then, of course, blue is precipitation on the left axis. And so there's a lot of things here that we can kind of talk about. You experienced all this, so I'm sure you have some sense of it, but it's worth kind of putting out there. First of all, the winter last year was relatively warm, pretty much like what we're seeing right now, but we ended up, at least in this station here, 2.1 degrees Fahrenheit above normal in last winter. Winter lows were in the middle of November and the middle of February. I was talking to a few people earlier that this early departures for cold temperatures in November potentially had some issues with affecting the vine through either minor bud damage or cane damage because they hadn't hardened off yet. So it's something to definitely consider. And then cold temperatures in February also were seen. We had 5 single-day records in Santa Rosa for precipitation during the winter. Most of those came in February, but also a little bit in January as well. There were some very wide swings. And when I say wide swings, I mean more than normal between temperatures. You can see the peak in April on the warm side, and then the drop-off into May, and then the peak again in June. Those are pretty wide swings for that time of year in terms of overall framework. We also had quite a bit of rain right during kind of bloom to set period, which I know Thibaut will talk a little bit about here coming up. We had a fairly near average summer here in terms of growing seasons. We were up 1.3 degrees Fahrenheit during the growing season. Growing degree days looked to be about 10 or 11% above average overall. However, we saw very few heat extremes. The ones we did, though, could have been quite impactful, especially in early June and then in late September. But only 4 records this past year, which is pretty low. And then, after that heat extreme in September, we had a pretty rapid cool down. Here, you didn't get much rain. Oregon would love to see the lack of blue there. We got dumped on in Oregon in September, October. But everywhere in the western United States cooled down pretty rapidly during that period. So just to kind of put this all into summary, kind of before I move off into where we are today. So first of all, part of our big influence that we had this past year was really what was happening in Siberia, Alaska, and Central North America. We're sandwiched in between. We had a really warm Siberian, Alaskan framework, and then a very cold Central North America. And I think that really did kind of squeeze us a little bit in terms of our climate. We had these major temperature swings, and this is part of that signature overall during April through June. We had a fairly warm, dry summer, but low heat stress, and I think that was pretty universal across the West. The North Pacific has remained quite warm, much warmer than average. I have a map showing this here in a minute. but that produces higher humidity, which tends to increase minimum temperatures overall. So it also brings potentially higher disease pressure. Intense heat followed by rapid cool down in September. I think that probably had some impacts from place to place. And that we did when I say south and north here, we're talking California, relatively large crop, but up north we had a relatively small crop overall. So let's go to current conditions and kind of where we are. So this is the current map of sea surface temperatures, just showing at any one given time where it's warmer and colder than average. The North Pacific continues to be relatively warm overall. It's displaying what's called a Pacific Decadal Oscillation positive situation, in which it's producing more moisture into the atmosphere than normal. The tropics have transitioned from a very kind of minor, weak El Nino to a neutral El Nino or ENSO right now currently. We'll talk a little bit more about what that means in just a minute, but the basic framework is that if you look at last year to this year, there are some differences. Last year on the 20th of January, we had a really warm tropical situation, so therefore El Nino kind of characteristics were feeding some of the rainfall patterns that we saw both in January and in February last year. This year, we don't have that. You can see the colder temperatures in the tropics, but you can still see the fairly warm conditions in the North Pacific. We do have some colder coastal waters off the west coast right now. Most of that's due to upwelling, but it's fairly shallow cold water, so most people think it's going to warm up pretty quickly as the season progresses. If you look at where we are from a water year perspective, going from October 1st to currently, we have temperatures that are fairly mixed across the western U.S. right now. California is up in general, while everybody else is kind of wavering around average. Interesting pattern, though, here that I think is quite telling is elevated areas are tending to be a little warmer than lower elevation areas, which is problematic for snowpack development overall. If you look at rainfall, I know you probably watch the news and everybody's saying, yeah, everything's good. Well, it really hasn't been that good. If you look at the overall water year precipitation percent of normal, this is going from October 1st to today. This is what we have right here. You can see that the west is largely dry. Southern California and the Southwest have seen some inputs. They've been a little wetter than average, but typically we're still running below average right now. So things haven't completely gotten better. We'll talk about that definitely a little bit more. Snow water equivalents in the basins across the western United States tend to be average to slightly down. Even though we've had reasonable inputs, it hasn't been enough to get us to average everywhere. If you look at California's snow water equivalents, we are currently averaging 40% of what we would expect to have by the end of the year in April, which means we've got a lot to make up overall. But we're still right now sitting at about 82% of normal snow water equivalents for this time of year. So we're in good shape right now, but we need inputs. That's the big point. We need some more snowpack development to happen between now and April. I don't know if you guys have seen this here, but I kind of follow this quite a bit here. This is the Northern Sierra Precipitation Index for 8 stations. And this just gives us the basic trace over the winter into the season. And currently right now we're sitting below average. Even though we've had some pretty good inputs, we're still below average right now. We're nowhere near what we were in the 16-17 wettest year, but we're also nowhere near the driest year either. So we still have plenty of time, but you know, we're definitely below average at this point. Wanting to put the drought monitor into framework. If you don't look at this, this is the U.S. Attempt to take all of this data and kind of tie it into kind of our conditions at the moment. We have a relatively low drought footprint right now. It's lower than it's been in a few years. However, there's some places that have been prolonged, like the Four Corners, where they've had a pretty extreme drought, and it's been there for about 2 or 3 years now. We also see Pacific Northwest in my region is seeing moderate drought. And early inputs this winter have been pretty good for California. The drought footprint here is virtually nothing right now. If you look at the reservoirs in California, Currently 67% of total capacity, meaning that they're doing some pretty good planning. They're holding water, but they're also releasing to keep room for inputs later on. It's 108% right now of historical group average for this time of the year. Slightly more than what we had last year at this time. Still plenty of time for rain inputs, but we need more snowpack, clearly. So that takes me to the last piece of this, given everything kind of we're seeing and what the models and everything are telling us, is to put that into a kind of a forecast framework. So first of all, the past few years have produced some pretty strong variability in weather and climate factors in North America specifically, but globally as well. We know from a climate standpoint that persistence in the climate system typically would point us to being continuing on the same path with a warmer year. However, well, as a matter of fact, let me go back to this diagram. The Met just released this, the Met Office in the UK just released this the other day. Their projections for next year are this year are forecasting us to be basically where we've been for the past few years. So they're really not saying that the planet framework of warming is changing very much in the coming year. However, I was talking with somebody at my table a minute ago. There is a wild card out there. You guys heard of the tall volcano erupting in the Philippines? Scientists right now are a little worried. That volcano, if it continues to erupt at the level that it is now for a prolonged period of time, like a month or 2 or 3 or 4, could mute temperatures globally throughout 2020 and 2021. So there's some geologists and geoscientists are really looking at that as maybe a major input into the system. So we have to keep an eye on that. Oops, that's weird. Weather extremes will likely continue near record numbers, and most of our modeling is showing us that we think that the northern plains and the southern tier estates are likely to see more extremes in 2020. We know that drought has declined, especially in California. However, you guys have probably heard this in the media. They've been calling this the ridiculously resilient ridge. The climate scientist, just the RRR. This is a big flip-flop between what happens between the West Coast and the East Coast. About a month ago, Seattle got 8 inches of snow while it was 74 degrees in Boston. That's kind of the basic framework behind this big resilient ridge kind of framework that creates flow paths between different characteristics of the United States. The southeastern United States this past year had a growing season during the middle of the year that was one of their driest and best on record. People in North Carolina say it was the best vintage ever. You should laugh at that. Come on, just a little bit. The North Pacific is warm. It's likely to stay warm, and this should lead to our continuing kind of framework behind higher humidity levels and higher minimum temperatures, especially over the western United States. If you look at some of the forecast data that's out there, this is NOAA's output. And while I have some trust into it, I can give you some caveats there. If we look at March, April, May, the temperature forecast in the diagram up top shows we have a greater chance for being above average in the West. However, I think there's going to be some pretty large month-to-month variation. Right now, everything is pointing to February and March being warmer than average, and April likely being cooler than average, and then May warming back up again. If you look at precipitation, the current forecasts are all tilting the odds to California and the Southwest being relatively dry. Eastern half a little bit wetter, of course, but Pacific Northwest staying kind of probably near average over the next couple of months. Both of these resemble kind of everything that our models out there are telling us about what happens when we don't really have the major El Nino impacts going on into the spring and late summer. So this takes me to the same U.S. drought monitor, but their seasonal outlook. This is what they're pointing to right now. Drought persisting in places in Oregon in the brown, the Four Corners region, getting a little bit better potentially in Washington and down into Texas. But everything in yellow is an area of concern where they think the drought will develop and stay with us into this growing season. So put this all into kind of a summary for the Western United States. This is just kind of going back everything that we've talked about to this point. The tropics are wavering around kind of neutral conditions, no real impact from either El Nino, La Nina in terms of those influences. The North Pacific is much warmer than average, as I've said. Both of this is showing that the atmosphere looks to have a split flow going into spring and mostly shunting storms to the north of us or to the south of us. You put these all together, and then what does this say? California, warm, dry, late winter, transitioning to a cool, wet spring. Pacific Northwest, kind of similar but more average, late winter, transitioning to a cool, wet spring. Spring frost frequency, I've just looked at data, trying to look at analog years to try to make some comparisons with it. In years like this, as we transition from January into a spring like this, spring frost frequency tends to be higher in these kind of conditions. The probability, of course, increases northward and inland, depending on kind of where you are. Growing seasons with these same kind of conditions leading into the summer tend to tell us that the persistence in the climate system would lean to 2020 being somewhere near the average of the past 5 years. I would say it's probably going to be closer to 17 and 18 versus 19, but there's no reason for it not to be somewhat close to that average. Increasing drought conditions in my area, is really a problem, and the forecast for late season decline in snowpack is really a concern. I think we have to watch over the next couple of months. So with all that, I wanted to mention to you that if you're interested in this, I've been doing monthly weather and climate reports for 20 years that I send out to about 3,000 people in the Western United States. If you want to get on that newsletter list, go to linfield.edu/wine and look for the reports on the left-hand side. And there's a little sign-up thing there for you to electronically sign up for it. These reports are really West Coast kind of oriented, but there's a little bit of more focus in Oregon just because I live there, but it's still more West Coast oriented. So with that, my voice managed to stay with me, and I appreciate it very much. Thank you. Tebow.
Thank you, Greg. I had a question. You mentioned the volcano eruptions disturbing the atmospheric conditions. Do you think there might also be some carryover effects coming from the Australian fires?
Potentially, but from what I saw from some estimates, and again, estimates, that if the volcano keeps erupting at its current rate, it takes like a week to have more input than all of the fire smoke coming from Australia would. And the other thing is that the particulate from a fire typically is short-lived in the atmosphere. The particulate is typically a little larger, where a volcanic eruption has smaller particulate that tends to get in the higher atmosphere. And that's where we think that it has a greater effect of reflecting energy away versus holding energy in. And by the way, the last volcano that had this type of potential and really did cause some issues was Pinatubo in the Philippines in 1991. We know that global temperatures were probably suppressed by about 1.1 degrees Celsius that year. So there's potential for that.
I just wanted to make sure I was clear that when you discussed through the second half of the slide sets, that when you said average, you meant 30-year average.
Yes. So it's kind of a challenge because you really like to be able to see the long-term record and to say how things deviate from it. And so I was saying in there that the 1895 through 2019 period, but most of the time climatologists always talk about the recent 30-year normal period. So 1981 to 2010 is the last 30-year normal. We are probably about a year before we get to the 91 to 2020 period. And what will happen is that we'll have to start talking a little different because we're in a new 30-year normal. Does that make sense?
It does, but I wonder if you ever look at data that pulls in those very dry years, for instance, 76 through 77, and if that skews things towards a greater standard deviation.
Yeah, it definitely does. So when I was showing the standard deviation, that was based upon the entire data record. Yeah.
My name is Nick Goldschmidt. I don't know how to ask this question. I live in Chile 30% of the time. Mm-hmm. The droughts in Chile have become extreme, especially in the Central Valley, and everything was relatively similar to California up until about 2 years ago. Is there a relationship between the temperatures of the ocean off, say, Valparaiso versus Seattle? Does it make sense? I mean,
Yeah, no, you're right. The Valparaiso and Seattle or Portland are analog climates because they have analog conditions, ocean temperatures, circulation, things like that. So there is some things very similar there. The only difference that really comes into play down in Chile, in Argentina, is the fact that the landmass narrows. So the fact that there's less landmass at that latitude does produce a slight different kind of framework in the circulation and how the continent versus oceanic influence happens. The other thing across that part of the world is that the Indian Ocean, Australia, and then the Central South Pacific all kind of interact together, which is a little different than what we see in the North Pacific. Does that make any sense?
Is there a record somewhere of the ocean temperatures off Seattle and ocean temperatures off Valparaiso?
I definitely have the stuff for Seattle off of the western United States, but I'm sure I could probably find it. I just haven't really looked at them simultaneously. But we can talk about that later, okay? There's someone.
Should we pay more attention to the Arctic or the ocean?
It's a good question. I personally think the Pacific Ocean is really a major driver. The mass and the amount of heat it can hold and how it can generate variations in circulation are really, really critical. But you can't discount that the Arctic has been really doing something. I didn't mention it, but I really truly think that we've been into a place lately where the Arctic has shown much more warmth than it has in a long time, and that has shunted colder air into different places like North America, potentially. There were times this spring that parts of Alaska and parts of Siberia were 60 degrees Fahrenheit above average, and they were actually warmer than we were here. I mean, it's just the system is pulsing in different ways, and it's places we've never been before, is really what it comes down to.
Tim Carl here. 3 real quick questions. One, when you did the UK, you presented the UK forecast.
Yes.
And, that trend line looks pretty steep. And then it kind of has this, you talked about this year. Could we just talk a little bit more about that in terms of the slope and that? The second question is, Pinatubo, it was 1.2 Celsius, Fahrenheit?
I'm pretty sure it's 1.2 Celsius, which is close to 2 degrees Fahrenheit.
And is there any data that talks about how long that effect lasted?
Yeah, most of the science behind it says that the effect was somewhere between 9 and 18 months.
Oh, then it just...
Yeah, then it kind of essentially dissipates, because if you think about it, all of the particulate that gets into the atmosphere eventually is going to fall out. But some of the smaller particulate can stay in suspension much longer.
And then in terms of this year, to the UK forecast, just back to that a little bit. What can we dive into exactly what it's saying?
Sure. So I've been following the Met Office in the UK. It's the Hadley Climate Research Unit. I know quite a few people that work there, and I follow their work because they've been really consistent for about 15 or 20 years on that forecast. They've been within their standard deviation over that entire time period. So what they do is about this time every year, they come out with their forecast for the coming annual cycle. And they are basically using what I've been talking about is the persistence of the climate system, the current state of the oceans, the current state of the Arctic and the Antarctic, and they put that into the model and project out over the next year. Now, they're projecting us to be at least 1, if not 1.1 or so standard deviations above average, continuing in that same kind of framework of where the past 5 or 10 years are. But you're right, the slope of the change has been really dramatic since the 1970s or so, 1980s. The rate of change has gone up quite a bit from the earlier period of record. And most people think that that is really just tied to the fact that we keep adding to the heat load, the radiation imbalance in the atmosphere.
What is that? Is it 3 degrees?
Let me see if I can go back. It might take a few booms here. There you go. So if you look at this, go back to 1950 or so. From the peak in 1945, we think is due to coal. The fact that we had a lot of coal going up into the atmosphere, warming things, but that the coal was dirty, and dirty coal had a tendency to cool things a little bit. So if you look at that 1940s to the 70s, we think that's due to dirty coal, sulfur, essentially. And so as coal cleaned up and we started using more of it and more other fossil fuels, we ramped up and took off from the 70s, and the rate of change is dramatically different. I can't remember the exact number, but in Celsius, I want to say it's like 0.9 of a degree Celsius per decade. It's pretty close, but don't quote me on that.
Any last questions? Time for one more.
Okay.
Well, thank you, Greg.
Thank you.